Okay, thanks a lot, Manju, and to all the organizers for putting this impressive workshop together and for having me here. So I'm going to discuss some work. This is a series of works I have been doing with my good friends Francesco Caravena from Milan and Ron Feng-Sun. And we have been doing these works mostly in the framework of disordered systems and scaling limits. And within these limits, there is a class called marginally relevant disordered systems. And actually, it turns out that the two-dimensional Kpz can fit into this framework of marginally relevant disordered systems. But let me first of all find my notes. Here, okay. Okay, so let me write down the Kpz equation that everybody knows by now. Okay, so this is this nonlinear stochastic partial differential equation driven by space-time white noise. And of course, this equation does not make sense, and nevertheless, it governs a large range of models. And in dimension one, even though this equation doesn't make sense, Kardar, Paris, and Zhang made some scaling analysis, and they predicted the exponents 1/3 and 2/3. Now, in dimension two, the situation is even worse than dimension one. Exponents are not known. And the message I would like to convey is that one reason possibly that exponents are not known is that making sense of the equation is much harder in dimension two than in dimension one. So if one would like to make sense of this equation, what would be the procedure? So the procedure will be to mollify the noise and then solve this smooth equation. And then try to take the limit as epsilon goes to 0. So what I mean by this W epsilon, by W epsilon, I mean you convolve the white noise with a smooth function, which, okay, in dimension, okay, some smooth function, which I'm not going to specify for the moment. And now you want to take the limit as epsilon goes to 0 and say that the solution to this equation has some limit in some sense. Now, of course, things will become very nasty. Yes? Yeah, this is only convolution in space, so yes, that's a good point here. So we smooth out the space, but the time is still rough. And so the standard procedure that is done, you need to subtract a constant C epsilon, which can be explicitly written down. And then in dimension one, that was the approach of Ayyer. He looked at this equation and choosing the C appropriately going to infinity as epsilon goes to 0, he was able to show that this has a limit. And that was the first example of the theory of regularity structures. Around the same time, there were two similar approaches in dimension one for the Kpz equation by Gubinelli, Perkovsky, and Imkeller, who built the theory of paracontrol distributions, and Kupianen. And also, we should mention that actually a sense of the one-dimensional Kpz was given much earlier by the work of Bertini and Giacomin in the middle of the 90s in relation to particle systems, a particle system approximation of this equation. And there were a few other treatments of the one-dimensional. There is also the notion of energy solutions by Hara and Gonzalez. And there was also some approach by Zygouras, who is another colleague at Warwick. Okay, but all this is in dimension one. In dimension two, these theories fail. dimension 2 is what in the theory of regularity structures or SPDs is called critical dimension. Now, what turns out to be is that if you would like to make sense to mollify the noise in space, and now I'm going to write what is this J epsilon of x will be 1 over epsilon squared. The 2 here has to do that you look at 2 dimensions. It turns out that you cannot give a meaning to this limit. So first of all, you have to renormalize the noise. So you have to multiply here the noise by beta times square root 2 pi divided by log 1 over epsilon. Then you multiply the mollified noise and you subtract the constant. And the constant basically is the quadratic variation of this noise, which I can write down explicitly. So it's going to be beta squared. Okay, let me remember. Two pi log 1 over epsilon. And then here we are going to have 1 over epsilon squared times the L2 norm of the function j. This 1 over epsilon squared comes from this scaling, and this comes from the strength of the noise. Okay, so this is the object I want to study, and say that in some sense we can have a limiting solution to this equation. Now, there is an equivalent formulation. So instead of renormalizing the noise, one can renormalize the non-linearity. So one can write the equation. I have an H tilde. And then you take the red part from the noise to the non-linearity. Now, this this form of renormalization was studied recently by Saurav Chatterjee and Alex Dunlap. But actually, the two forms of renormalization are equivalent. Basically, we have the relation that H epsilon, H tilde epsilon, minus its expected value is equal, let's forget about the expected value, H tilde epsilon is equal to 1 over beta epsilon times H epsilon. And the beta epsilon is what I'm going to abbreviate this constant with. Okay, so obtaining a limit for this equation is the same exactly as obtaining a limit for this equation. Now, the theorem I'm going to state is the following. So this theorem, you can think of it as having two parts. The first part is about the one-point distribution. And that was actually in a work we did with Caravena and Sun in 2017. And it goes as follows. So now I'm going to just concentrate on this form of the solution. So there is a critical parameter beta, which can be explicitly computed to be equal to 1. And if we look at the solution for fixed t and x, if we look at the solution to the Kpz equation, then as epsilon goes to 0, this will converge in distribution to either a Gaussian, so I'll have some variance standard deviation sigma beta. This is a Gaussian standard normal variable. So this will hold if beta is strictly less than the critical parameter 1. And if you are at or above the critical parameter, this will converge to minus infinity. And the sigma beta can be explicitly written to be log 1 minus beta squared to the negative 1. Okay? Now, of course, this minus beta, minus infinity, is not very satisfactory. So this actually calls for the very interesting question: what do you need to add to the solution to the two-dimensional Kpz equation for fixed t and x in order to get away from minus infinity and find the scaling limit? Now, the second part of this theorem was actually motivated when we saw the paper of Chatterjee and Dunlop. No, you don't need it. The normalization is done here. So the second part of the theorem, so that was done last month, that was completed last month, looks at the solution to that equation as a field. So what do we mean by this? So we fix t, and then we average when we center accordingly over some test function. So we average only in space. And then we multiply by log 1 over epsilon divided by 2 pi square root. So basically by the inverse of this factor. And what we have shown is that as epsilon goes to 0, this will converge in distribution to the average over another random field. And this random field is a solution to the additive stochastic heat equation. And what is important here is this prefactor. So you already see that this convergence can only be meaningful for beta less than 1. Now, a couple of observations are the following. So if we look at this version of the equation, here you scale down the nonlinearity. Okay? So naively, you may think that the limit of this solution will be the solution to the equation without the nonlinearity, if you just erase this part. But actually, our theorem says that this nonlinearity actually produces some non-trivial noise, which goes and you see it at the end and the limit. So the nonlinearity is not completely non-trivial, not completely trivial, even in the subcritical regime. And a second comment is a remark actually by A.J. Chandra and Martin Ayyer, that the fact that in the limit we see a solution driven by a noise with different covariant structure actually indicates that the solution to the Kpz equation, either this form or that form, cannot have a strong solution in the sense of stochastic differential equations. can have a weak solution, and that's why we have a limiting distribution, but cannot have a strong solution because a strong solution actually would be measurable with respect to this noise. This is a different noise and actually has different strengths. Okay, so maybe I'll start now unraveling how we go about this part of the theorem. So originally, within this work, we were looking at the Hopf-Kohl transformation. Yes? Yes, so this will come later. Yeah. It will come later. Okay, so we were looking at the Hopf-Kohl solution. Basically, if we set U equals, no, H equals log of U, that's called the Hopf-Kohl transformation. And U will solve the stochastic heat equation with multiplicative noise, at least formally. And if you go by Feynman-Katz formula, the solution to this equation can be given in terms of a continuum polymer, or in the discrete version by a direct polymer model. So the first theorem we had was that let's look at the solution to this equation where we smooth out the noise. And then let's look at the limit of this. So we can, 1 point, so fixed t and x. So the solution will converge in distribution to either a log normal, which will be the exponential of this, if beta is strictly less than 1, or to 0 if beta is greater or equal to 1. So you see, for the 1 point function, then passing from the stochastic heat equation to the Kpz equation, it just amounts to take the log. And that's all. And that's why you see the normal, and that's why you see the minus infinity here. And a second result we had was about the limit of the solution as a field. So we take U epsilon, we normalize we center by 1, and actually this one, you should think of it as the solution of the heat equation with a flat initial condition equal to 1. So actually here I didn't mention the initial condition, so the initial condition is 0. And the initial condition here, we can take it to be 1. We can also have other formulations, but we take it to be 1. So this one here will be the solution of the heat equation with initial condition equal to 1. And then we test it against the function. We multiply by log. And this will converge to the solution of the additive stochastic heat equation for beta strictly less than 1. So we also had another result. So this tells you what would be the correlations if you look at the solution at basically diffusive scaling, if you look correlations at diffusive distances. We also had another result saying that if you look at subdiffusive distances, then the field is non-trivially correlated. And it has multi-scale correlations at all scales. For any exponent, let's say, n to the power xi, for any xi less than 1/2, you have a correlated field. Okay. And yeah, okay, of course, now again, we have the interesting questions. What happens at or above criticality? So in this setting, what do you need to multiply in the solution in order to see something non-trivial? And over here, there are some similarities with Gaussian multiplicative chaoses that can give maybe some intuition. Over here, what should be at beta equal 1 should be that you should forget about the scaling, and you should have a limit, which we don't know what it is, as epsilon goes to 0. But we know that the limit will be log correlated, but not Gaussian. Okay. So this is the overview of the results I would like to discuss. And now I would like to give some ideas of how we went about it. So we looked basically at, we were looking at the discrete partition functions. So, and the relevant discrete model for the stochastic heat equation is the partition function of the direct polymer model. So let's look at Zn equal the expectation with respect to a two-dimensional random walk. Here you sum, your field is a bunch of IID random variables, which is a discrete analog of white noise. And you sum it along the trajectory of a simple random walk. You multiply by beta n, and then you subtract the log moment generating function of omega. In the case of Gaussian, this would be 1/2 beta n squared. So we can also look at this starting at some point x. And basically, the results I stated there, they translate for the partition function of the direct polymer. So if you look at the limit of Zn when beta n is chosen to be beta, actually here is pi divided by log n, and the pi has to do with the difference between pi and 2 pi has to do with the periodicity of the simple random walk. Then the partition function of the two-dimensional direct polymer will have this limit for n fixed x. While if you average with respect to some test function, it will converge to Gaussian. Okay, so I will now essentially concentrate on this, show you the expansions that we do for this type of partition functions. The role of beta n and the choice of beta n will come. And this approach is quite robust. So actually we had a more general theorem saying that if you have a partition function of what can be called as marginally relevant disorder system, and we can define marginally relevant in the sense of you look at the overlap of the pure system. So in this case, you look at the expected number times of intersections of two independent random walks. If this grows as a slowly varying function, then we can name this marginally relevant. And this behavior, this limit theorem should be valid. So for the moment, we have this limiting behavior for polymer type models. But one can think also there's a marginal model in the Ising, the energy field of the Ising model, and one can come up with other such kind of statistical mechanics systems. Okay. Before going into how we treated that partition function, let me make some remarks. So here, so why passing from this limit theorem to this limit theorem is not immediate? Well, So I told you that h epsilon, you can put it to be a log of u epsilon, right? So you want a limit theorem for h epsilon. Here you have a limit theorem for u minus 1. So you can think that this is so you approximate the log, you do a linear approximation of the log. But this actually is not correct. There are two reasons why. There is one reason why it's not correct, and another reason which actually proves that this approximation is not correct. The reason why you cannot do this naive approximation is that the field here is log normal, so it will not be close to 1. But you can say, okay, it's not close to 1, so this naive approximation doesn't work, but maybe still, right? After all, the limit theorem here is exactly the same like the limit theorem here. Well, except for the fact of the centering constant. So this centering constant actually turns out to be 1/2 this sigma beta square, and actually this shows that there is some kind of critical non-trivial shift, which proves that the naive approximation cannot work. Okay, so let me now go and discuss how we proceed with these proofs. Okay, so first I will start with a sketch of the method for the theorem of the stochastic heat equation, and then I will describe how we can go ahead with the approximation, given some intuition we can gain from the stochastic heat equation. So the first step of the method is to do what is called a multilinear expansion in stochastic analysis, or in statistical physics, a Ayyer expansion. This amounts basically starting by taking the sum as a product, and then adding and subtracting 1. So I will replace Sn by x, and then I will also have here, you can replace Sn by x, but then you have to sum up over all possible values of x times the indicator that Sn equals x. Okay, so we can write this. So here I subtract the 1. In the numerator, you will have an indicator that Sn equal to x, but because this is a binary function, it takes value 0 and 1, you can bring this down below the exponent. And I would also like to normalize by dividing by beta. Beta will be beta n, right, eventually, and multiply by beta. We close the expectation, and here is the product over all n and x. And we will call, as a shorthand notation, this random variable psi nx. So the lambda beta is a log moment generating function for omega, so this makes this random variable mean 0. And if it is Gaussian, if the omega is Gaussian, this would be variance 1. If it is not Gaussian, when beta is small, which will be the case, this will have asymptotically a variance 1. So for all practical purposes, you can think of this as a mean 0, variance 1 random variable. And then we expand this partition function by basically multiplying out this product. It's nothing more than multiplying 1 plus a times 1 plus b equals 1 plus a plus b plus ab, and so on. So we can write this as 1 plus summation k greater than or equal to 1. Let me just insert the beta n, because the next step will be how to choose a beta n. And then we sum n1 less than nk. We also sum points x1, xk. Now we will have the product S1 equals x1 times Snk equals xk. and the product xi and I. And the product of the noise random variables. Okay. So that's an expression, and the question is, can you find the scaling limit for this expression? Now comes the choice of beta n. So how to choose a beta n? So let's look at the first term in the expansion. So that would be n equal 1 to capital N and summation over x. Here you will have basically the probability that a simple random walk at time n is at location x times the random variable psi nx and times the beta n. So you would like, if there is any chance that you can have a limit theorem, this to be tight, so the variance of this to be of order 1. So you can compute the variance. This is the sum of independent random variables, so you'll have beta n squared, a summation n equal 1 to n, summation over x, the square of the transition probability. And here you can see the overlap. This quantity here is the overlap. In the two-dimensional random walk, this blows up like log n. So basically, for this to be order 1, beta n has to be chosen like 1 over square root log n. And in general, what we call marginally relevant systems is when this overlap here, when you do this expansion, this overlap grows up like a slowly varying function. And the slowly varying function is very crucial to have these limit theorems. Okay. A second observation is that if you do this logarithmic, if you do this computation, then you can ask the question, okay, I want to start changing my system. Instead of having a system of order n, I can have a system of order nt. How this will change for large n. But because of the multiplicativity of the log, any linear change in time will not be felt for the system. However, a change will be felt if you look at exponential scale. Because then this t will come down, and then you'll start seeing a linear response to your system when you change the system at an exponential scale. So this indicates that the correct time scale is n is exponential, n to the t. Okay, now you have this ingredient. Okay, so you would like, again, to find out what is the scaling limit of each one of these terms. Then it would be the question how you can patch all of this together. But the first question is, what is the scaling limit of each one of these? So this term, actually, is very easy. You can do a Lindeberg theorem. It's a linear functional of the noise. So this would be Gaussian. That's trivial. The interesting part is when you look at the second term. Okay. So I'm going to use a toy model. So you can imagine that we can sum out the space variable. And then I only want to deal with, just for the purposes, but actually that's also the way we came across this. So think that I have summed out the space variable. And the relevant, when you sum up over the space variable of the heat kernel, eventually you will have only a time dependence, which is like square root n. So if you can think of this as like, if you prefer, just think of this as a toy model, but can come from the two-dimensional polymer by summing out the space. Okay, and then you want to ask the question, what is the scaling limit of this? Naively, so this log n is chosen so that the variance of this is of order 1. So this is a tight random variable. Naively, if you just replace sums by integrals, the ID random variables with noise, you could think that this will converge to but actually this is not sensible because this integral does not make sense. The L2 norm of this is not a well-defined Ito integral. The L2 norm of this blows up like 1 over t. So this is not a solution. It's not a scaling limit. And so actually here we scratched our head quite a bit. There is something called the fourth moment theorem. The fourth moment theorem is attributed to Noah, and Pecati, but actually you can trace it back in studies of statistics in the 60s, and it was rediscovered in the 21st century. So it says that if you have a multilinear form polynomial like this would converge to Gaussian if the fourth moment converges to 3. So initially we thought, okay, let's just compute the fourth moment of this. There was a long computation, but the fourth moment was not 3, it was 6. So then we had to start, wondering, and after a number of crazy heuristics, so the guess was that the limit. Okay, so here we do this important change of variables. So if you do this change of variables, n1 equals t1, n to the t1, n2, n to the t2, then you will have an iterated integral of one-dimensional noise when t1 is less than t2, and an integral of a two-dimensional white noise when t1 is bigger than t2. It actually turns out that the fourth moment of this is equal to 6. So that had to be the answer. Okay, then we had to figure out the third case in the term. And once we figured out the third case, which is a mixture again of noises of different orders, then we could figure out everything. And the role of beta being strictly than 1 had to do with being able to patch all these limits together. Also, you can see the role of beta being less than 1 by computing the second moment of your partition function, and then one can see that this blows up at beta equal to 1. Okay, so this this result can settle this theorem, and essentially also the theorem for the field, for the stochastic heat equation. Now, how can we pass from such a theorem to studying the log of the partition function as a field? So let's say log of Zn. Okay, there are two pieces of intuition that come into play. The first one has to do with this time scale. And this one indicates that when we look at the scaling limit, the distributional limit of the one-point function for fixed, let's say, space and time. Here I don't have a time, but you can also put a time. So the main contribution to fluctuations of one-point function comes from disorder in a neighborhood of n times little o of 1 of the starting point. So if you want a picture, you start your polymer at some point x, you let it run by time n, but the noise that actually will contribute to the fluctuations will come from a small area. Right? And again, this has to do with the fact that if you look at this variance between, let's say, a times n and b times n, right? So you will have log bn minus log an, and then you will not have any contributions. Okay. Now, however, for the field fluctuations, I mean you have a polymer starting, let's say, at some location x1, maybe x squared root n, and y squared root n. So this is a distance n. So this would be essentially independent unless the polymers start they meet. And then they start sharing some common noise. But if they start at distance n, square root n, they can only meet at some distance of order n. And actually, the probability of this event to happen decays like 1 over log n, which this actually explains why, when we look at the averaged, we need to multiply by log n. Right? So that computation there explains why beta n has to be chosen like 1 over log n. And this explains why, when you look at averaging, you need to multiply by square root log n. Also, the beta less than 1 is important because when the two polymers meet, essentially you will be computing the second moment. And for beta less than 1, the second moment is finite. On the other hand, in a paper we wrote in August, and took us quite a while to complete, at beta equal 1, this second moment actually you start blowing up like log n. Right? So this log n will cancel the 1 over log n, and that's why in the beta equal 1 case, you should have a limit theorem without multiplying with something. Okay, so we have these two pieces of intuition. If you look at the 1-point function, the main contribution comes from a small area, little o of n, of the starting point. If you look at the average, the correlations, then you start feeling the noise at scales n. And now let's put these two pieces of information together to see how we can do the approximation. Okay, so what we want to approximate is basically log of Zn of x when we average this. So here, this factor is the Riemann sum approximation for this one. And then here, let's just put square root log n. Okay. And now we want to approximate log of Zn by something that only has a partition function. Okay, so now we start, let's say we have a point x, and we know that if we look at log of Zn, we'll write here, the main contribution will come from this area, which let me call an, and this is n to the O of 1, which I'm going to take to be an, and this an will be like 1 over log n to the 1 minus gamma for some gamma which has to be chosen so that estimates work. But okay, this is just keep that this is something that goes to 0 with n. Okay, so then we can split the partition function to the partition function when the disorder is concentrated in A. So when I do the multilinear expansion, right, so when we do the multilinear expansion, we have, you pick n1, x1 here, and then you pick a noise n2, x2 here, n3, x3 here, and then you sum these noises with some weight, which is a transition kernel between the points. Okay? So here I assume that ZA is a partition function where disorder I only sample within this box. And then the rest I'm going to call hat. And when I look at the one-point distribution, this will be much larger than this in some second moment variance sense. So I pull this out. And now I do Taylor expansion here, because this is going to be small by the intuition I have gathered from these theorems. So now we can write this as log ZNA of x plus the ratio plus some error term. So this error term will be the second order in the Taylor expansion. It will be a second moment. We have to do some estimates, and for this, we have to combine two tools. One will be actually a sharpening of hypercontractivity, and the other will be some concentration results that will ensure that all negative moments of the partition function are under control. Okay, now we have this expansion, but now when you average, this will have a negligible contribution because this has noise concentrated in a small neighborhood, but when you average, the main contribution comes when you are far away. So when you average, this will have a negligible contribution. Okay, this is an error, and now we need to deal with this one. So here the annoying thing is that it is a ratio. So it's not a partition function, it's a ratio of two partition functions. But we can, let's start to see what's going on. So the ZA will, okay, the ZA samples things inside the box. The Z hat, so I'm going to enlarge this a bit, samples things inside, possibly, but definitely will also sample things outside. And the main contribution will come when this is of order n, when this point is of order n. So, yes, let's move here. So this would be the partition function Z hat. But because this is of order n and this is of order little of n, this point cannot, will have a weight which will be the heat kernel. Let's call this point my, and let's call this point nx. So this will connect these two noises by the probability that the walk moved from time n location x to time m location y. But this cannot see that this is not something different than the origin. So basically, this will be almost equal to Pm y. Okay, because m is much larger than n. So this would be the same as if this field was connected to the starting point. And then, you can also sample more noise here, can continue. So basically, this approximation shows that Z hat of x will be almost equal to what? This, the noise, the sampling here, which is basically ZA, times the sampling of the noise outside. Let's call it Z outside. So of course, when now you divide by ZA. These things cancel. And then essentially, you can approximate eventually your log of Zn by a partition function of a directed polymer, two-dimensional directed polymer, where essentially, because this is very small, right? Essentially, it's also the original polymer. And then you cannot actually, you can go back to the machinery we developed in order to prove the central limit theorems using these fourth moment computations and some combinatorial analysis to prove the central limit theorem for this one. And yeah, basically this completes the proof and the talk. And thank you for your attention.